NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams. And all these little dots are stars?
All these little dots are galaxies, some of which are bigger than our own.
Breaking news. We may have just found potential evidence of intelligent life beyond Earth.
This is a huge discovery, and we think that it's a huge discovery. And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Well, JWST is so phenomenal that if you spend enough time, you could probably find any galaxy that ever formed in the universe. It's really that powerful.
NASA's James Webb Space Telescope has barely woken up, and the universe is now more baffling, more gorgeous than mankind's fantasies. This multitude of little specks are stars, and this multitude of little dabs are galaxies, some of which are greater than our own. Letting the cat out of the bag, we might have recently found expected proof of intelligent life beyond Earth. This is an immense revelation, and we imagine that it's a gigantic disclosure. That is the most thrilling piece of this telescope, this momentous instrument we've put in space. Finding things that we didn't expect and can't explain. That means we have to rethink our understanding of the universe. The James Webb Space Telescope, JWST, is so powerful that, if you spend enough time, you could probably find any galaxy that has ever formed in the universe. It's truly that strong. Pluto is a distant and mysterious, yet subtly fascinating planet that was once a part of our nearby planetary system. However, recent pivotal statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning discovery. They suggested that this cold world is on a potential collision course with Neptune. But how could this happen, and what might be the consequences of such a massive event? Are we witnessing a fascinating cosmic phenomenon, or is there more to this looming celestial encounter? Join us as we explore the potential outcomes of a Pluto-Neptune crash. Pluto, a former planet that was reclassified as a dwarf planet partly due to its unique orbit, remains a subject of interest and study in the astronomical community. According to recent assessments by leading scientists, Pluto's orbit is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially dangerous collision between these two celestial bodies, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's orbit around the Sun is unlike that of any other planet in our solar system. It requires a staggering 248 years to complete a single revolution. Since its discovery in 1930, it hasn't even completed one full orbit. However, the intrigue doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, differing significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unique is its inclination of 17 degrees to the ecliptic plane. The way Pluto follows its path is far more extreme compared to the other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's orbit. For about 20 years in each cycle, Pluto actually comes closer to the Sun than Neptune. Defying what we might expect from their positions in the solar system, this raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers sought to understand its unusual trajectory. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and elongated shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amid these complexities is a testament to the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects, like Pluto, Neptune, and the Sun, move and interact with one another through gravity. It's like predicting their movements based on their initial positions and gravitational interactions. For Pluto, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex manner. Terms like azimuthal libration and degree libration, along with the VZK wobble, are crucial to this puzzle. According to astrophysicists, what keeps all planets in their orbits is azimuthal libration. For Pluto and Neptune, this means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is essential in preventing their orbits from intersecting. Degree libration, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, adding another layer of safety from potential collisions. Another significant aspect is the VZK wobble, named after three scientists, Vazel, Zov, and KV, who studied how objects move in space. It describes how three celestial objects, like Pluto, Neptune, and the Sun, gravitationally interact. This gravitational interplay affects their movements. For Pluto, the VZK wobble explains why its orbit around the Sun is so peculiar. Despite its seemingly erratic trajectory, this wobble ensures that Pluto moves smoothly over long periods. The VZK wobble demonstrates that, although things in space may appear chaotic and unpredictable, certain patterns and forces maintain order. These factors help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or drift off course. This three-body problem is critical to understanding how orbits evolve due to the interactions between celestial bodies. Studying this not only helps us learn more about Pluto and our solar system but also about distant planets and their stars. Mathematical simulations in the late 1980s revealed that, despite these stabilizing properties, Pluto's orbit is highly chaotic. Minor deviations in initial conditions can lead to significant changes over centuries. However, the remarkable properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, mitigating chaos. Later computational models have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, affect Pluto's orbit around the Sun. Neptune, in particular, has extraordinary gravitational influences. The relationship between Pluto and Neptune is such that, for every 2 circles Pluto makes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. Anyway, Neptune isn't the main player in this. Jupiter's gravity likewise plays a crucial role in stabilizing Pluto's orbital motion, as does Saturn. These generations show that Jupiter's gravity alone is sufficient to ensure Pluto remains on a steady path for an extraordinarily long time, even for millions of years. So, perhaps Neptune, Jupiter, and Saturn are collaborating to ensure Pluto continues to move safely in space without running into trouble. These dynamics are fundamental for maintaining order and stability in the solar system. Without these elements, the solar system as we know it would be a far more chaotic place. Bodies like Pluto could collide with others or be ejected from their stable orbits, triggering a chain reaction with other celestial bodies. For Pluto, particularly with discussions about it potentially colliding with Neptune in the future, understanding its orbit is vital. This gives a clearer picture of the dynamic nature of the solar system. The case of Pluto demonstrates that even the most seemingly unstable orbits can reach a state of harmony through the complex interaction of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and analysis of these phenomena to better understand our position in the universe. Exploring the depths of space often leads us to confront the peculiar nature of celestial bodies, and Pluto's orbit is a perfect example of this peculiarity. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly illustrated with Pluto. This means that even slight changes in the dwarf planet's position or speed can drastically alter its long-term orbit. Using computational models has been immensely helpful for scientists in figuring out how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects like Neptune pull on one another. By tweaking small details in the simulations, astronomers can see how even tiny changes can have a significant impact on where Pluto ends up. In the late 1980s, these simulations revealed something fascinating about Pluto's orbit. Despite having mechanisms like axial tilt and orbital resonance to keep it stable, its orbit can still be unpredictable and chaotic. Starting with just a small difference in Pluto's position or speed can result in a completely different trajectory over several years. However, even with this chaos, Pluto's orbit remains stable over remarkably long periods, like billions of years. This means that Pluto's journey around the Sun has a kind of order to it, even though it appears chaotic at first. Predicting celestial events, especially when they involve irregular orbits like Pluto's, is a massive challenge. The inherent unpredictability of these systems means that long-term predictions are often fraught with uncertainties. While mathematical models provide valuable tools to understand and predict the future paths of celestial bodies, they also highlight the limitations of our predictive abilities. These models heavily rely on the accuracy of initial conditions, and any small error or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the chaotic nature of planetary orbits like Pluto's reminds us of the ever-changing and dynamic nature of the universe. While we've made great strides in understanding space, Pluto's case serves as a humbling reminder of how limited our knowledge of the universe still is. Understanding the gravitational effects of the giant planets on Pluto's orbit provides significant insights into the broader dynamics of the solar system. It shows that the presence and position of each planet can significantly affect the stability and trajectory of other bodies within the system. So why are prominent astrophysicists recently raising concerns about a potential collision between Pluto and Neptune, despite all these intricate forces working to prevent such an event? Neil deGrasse Tyson, a prominent astrophysicist and a major figure in promoting cosmology, offers an intriguing perspective on the mysteries of our solar system, particularly the fascinating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public's interest in the mysterious realms of space. Tyson's stance on Pluto's renaming is based on the ever-expanding knowledge of our solar system. He views the renaming not as a demotion but as a significant adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of constant learning and adaptation. He sees the complexities of orbits like Pluto's as a reminder of how much there is still to discover in space. The interest in these issues keeps the exploration of space so exciting. However, despite Tyson's optimism, his thoughts on Pluto's possible collision with Neptune paint a more uncertain future. He emphasizes that the orbits of Pluto and Neptune will continue to evolve, driven by forces that are sometimes unpredictable. Interestingly, Tyson also mentioned that these uncertainties could potentially lead to Pluto approaching Neptune's orbit over the next few million years. Despite this, he remains cautiously optimistic about the likelihood of such a collision. Tyson's analysis suggests that while the chances of such an event occurring are low in the short term, the unpredictable nature of planetary orbits means we cannot entirely rule out the possibility of such an impact in the distant future. In addition to Tyson, Michio Kaku, a renowned theoretical physicist, also weighs in on the implications of a potential collision between Pluto and Neptune. Kaku's analysis combines cutting-edge physics with a deep understanding of cosmic evolution. He believes that such a collision, if it were to occur, could have profound implications not only for Pluto and Neptune but also for our understanding of the universe as a whole. According to Kaku, a Pluto collision might trigger a cascade of other events, potentially even altering the nature of the solar system as we know it. However, Kaku also acknowledges that the likelihood of such a dramatic event happening anytime soon is very low. He points out that while the orbits of Pluto and Neptune are in proximity, the vastness of space and the complexities of their orbital dynamics make a collision improbable in the short term. Nonetheless, the possibility remains a fascinating subject for further study and speculation. Overall, the possibility of Pluto colliding with Neptune remains a hot topic of active debate among astrophysicists. While the mechanisms of their orbits prevent a collision from happening in the near future, the complexities of celestial mechanics mean we cannot rule out the possibility of such an event in the distant future. The ever-changing nature of planetary orbits reminds us of the dynamic and unpredictable nature of our universe. Whether such an event occurs or not, it serves as a fascinating example of how much we still have to learn about the future of the solar system.